Okay. So, any questions before we begin? Last time I ended with what?
Assembling charges.
Yeah, assembling charges. And we had a couple of expressions. If you have isolated single charges, it was 1/2. And please tell me if I'm right. I equals 1 to n. J is also equal to 1 to n, but there's a caveat, J not equal to I. Qi, Qj, Rij. And that got translated to 1/2 Qi V at the location of V due to the other charges. And this is a feature I want to come back to and I'll show you how this becomes a problem. It's an easy thing to fix. And in the continuous case, these both give what? It becomes a rho V d tau. Well, what volume do you include? So suppose I have charges in a, so when I use the integral expression, I won't show isolated charges, I'll just show like a bulk charge, or even a sheet charge or line charge is fine. But if you have individual charges, you have to tack this on, okay? So if, suppose you have rho here. By volume, I mean any volume that covers all of this. If I go outside, who cares? Rho is 0. So I can pick this could be my volume or smooth surface. Yeah? But I couldn't cut it this way and miss out on some of them. Okay? So I suppose one way to, I don't want to, overburden you, but I should write this as d tau plus 1/2 Qi V R I. This includes the continuous charge distribution, and this includes the, so hang on to this. Your book doesn't write, does not make you really focus on this, but we'll have one problem to illustrate the point where for the continuous part we use this, and for the discrete part we use this, okay? So hang on to that. Again, the volume is any volume that includes all the charges. Anything more is fine because rho is 0 in that region. Okay, so now suppose we have managed to, maybe using delta function and whatnot, write everything in terms of this expression. Okay, so focus on this one. W equals 1/2. There is a nice way to see where the charge is stored. Now where the energy is stored. Okay, this is an expression for the energy work we have done to assemble the charges. Now in doing so, energy is stored. And one interpretation is the energy is stored in the field. Well, which field? The electric field. So let's compute. So we're sort of transitioning to a field theory. We're replacing particles with fields, yeah? So let's try to see if I can write this expression with only fields in it. So what I'm going to do is I'm going to replace this with what? What could I replace this with? Can I do that? Because divergence of E is rho over epsilon naught. And then what I'm going to do is the following. I'm going to write divergence of a scalar function V times the electric field is, well, I don't know if there's no need for this parentheses. And, well, maybe here. That's equal to gradient of V dot E plus V times the divergence of E. Just the product formula. Again, from the inside cover. And this is precisely what we have. So I can write this to be this minus that. Yeah? So W is equal to epsilon naught over 2 divergence of V E d tau minus epsilon naught over 2 gradient of, in fact, bear with me, I'm going to put this. I just took the minus in here. First of all, when I bring it from here to here, there's a minus sign. Instead of putting it outside the integral, I just put it in. Because why? Negative gradient of V is nothing more than E. So, work is equal to, oh, this is plus then, epsilon naught over 2 E squared d tau. No, just this term. This is E dot E is E squared. Here what I'm going to do is use the divergence theorem and replace it with, tell me, who recalls what I should replace it with? The what? Correct. It would be V, very good, E dot dA on the boundary of that surface. So you should write what I write here at the end of this lecture, not quite yet. So I'm going to replace, this is a useful one, this is a useful one, and I'll have a simple, E squared d tau plus epsilon naught over 2 V E dot dA. That is another version. And final version, what I will do is I will integrate over all space. And then, that means, how does this come about? So this integral comes about by, again, my charge being in some region. This is rho, and this This is the volume. Yeah? And this over here is the, well, let me do it this way. dA, boundary of this volume. The volume is inside. It includes this as well. Now what I'll do is integrate over all space. So I will write that down explicitly as E squared D, and I think I wrote this before, but I didn't, I'm just assuming that you are familiar with the math notation. I used R3. Do you know what I mean by R3? All of XYZ. That means I'm going infinitely far away. Infinitely far away for compact sources. Remember, we're really doing, otherwise none of these integrals will converge. You don't have charges filling the entire universe unless we're doing exaggerated some problems like, well, you have an infinite plane of charge that, they're shipping that from Chicago. They haven't finished packing yet. Yeah. So what happens if you have a compact source like this, and you go infinitely far away? What happens to E and V? Goes to zero. So for today's lecture, you can recap it in your notes by rewriting all these three and understanding the context.
So then why does our second term went to zero?
Yeah.
Why is our first term not?
First term is also the inside part. So over here, indeed, if you go far enough away, this might go to zero. But we're also integrating the volume. This is only integrating the outer area. This leads to a nice interpretation. The energy density of the electrostatic field U is a symbol for that. Well, energy density is something such that when you integrate it over all volume, you get the total energy. Well, what is that? Oh, let me write this in 1/2. So you say that one could interpret this as the energy stored in the field. Where is, when you assemble charges, where is the energy stored? It's stored in the field, the electric field it creates. Yeah? Well, what's the energy? Well, energy you have to integrate, but the energy density is 1/2 epsilon naught E squared. You can see how this looks like 1/2 mv squared. That is only just a crude statement. You do not take any deeper meaning from that. But these are all quantities like energy. Yeah. Very soon, perhaps in this chapter, I mean this semester, if not next, you'll have energy density due to the magnetic field. What do you think that's going to be? 1/2 b squared with a different constant. Don't worry about that constant. Instead of epsilon naught, you'll get mu naught. But turns out it's in the denominator. Yeah. This is where the energy is stored. I will upload a problem that I've done in detail that uses this and this. Okay, just one simple problem. And you can expect problems generally to be like that. Now, I didn't mention, if you take this too seriously, you might get into a little bit of a problem for isolated charges. What happens if we calculate the energy required to assemble a single charge by this expression? It's sort of silly because that's not what we're talking about. A charge, does it see its own electric field? No, it sees electric field only due to, yeah? So just, it cannot see its own electric field. Remember, because at its own point, the electric field is 1 over r squared, that's 1 over z squared. I'm sorry, 1 over 0 squared. You don't want that. And exactly, that will create the problem that we don't want. That's why I have not suggested, that's why the math tells you, you have to add those guys separately. But let me show you, in fact, that when you do this, you get infinity. The energy due to a point charge, and this is a silly question, so I'm going to, just over punctuate, exclamation, question mark, quotes, exclamation point. This is silly. We're not talking about charge creation. Yeah, how is matter created? It's still an unsolved problem. Infinite, yeah, maybe infinite energy is required to create something, but for us, it's already there. Yeah, this is the problem of free normalization in quantum field theory, where we know how to do this, where we can remove infinities in a meaningful way. Removing infinities is just bad business, because you cannot distinguish 1 times infinity from 2 times infinity. So what have you really removed? Did you remove twice as much, or half as much? Yeah? It's also a big problem. But we're not going to be thinking people today. We're just going to crank it out. Just to show that there's a problem with looking at the universe in a naive way. E squared, kq over r squared, squared. Right? Kq over r squared, just a magnitude, d tau. And you can see r squared sine theta, d theta, d phi, dr. I can do epsilon naught over 2, k squared, q squared. I can do sine theta, d phi, which is 4 pi. And then, all of a sudden, you have r squared dr from 0 to infinity. And that, I'm afraid, approaches infinity. What's the integral of 1 over r squared? Minus 1 over r. If you evaluate that at 0, what do you get? Infinity. Yeah? These are all things that suggest greater problems. That's why I'm mentioning this. Another big thing that one finds while studying the other extreme case, the entire universe. Remember, we want our sources, charges to be compact. We're studying charges on Earth or on a star or whatnot. But if you're studying cosmology and the entire universe, there's a quantity called the cosmological constant. It's supposed to be a small number. But you do any calculation, what do you get? Infinite. So it's perhaps maybe the vacuum itself. It's a property that space-time has, the cosmological constant. Every point in space has that, space and time has that. So, but if you calculate that, any meaningful calculation is, it's infinity. These are all unsolved problems. This has been perhaps better understood in quantum field theory, but the problem of cosmological constant continues to elude us. There are certain infinities that come to us that is puzzling. Yeah. Any questions? So you deserve a sample problem, and it'll be entered. Any questions? Everything clear? We should be. Yeah, Chip? Huh, what's that?
You were asking us questions, and we were saying, well, what if you rolled a charge in the shortest possible time? We were just like, you know, that's like a mechanics.
Oh,
question.
that's like a banquet question.
Yeah.
I'm hoping you're equally traumatized by your mechanics course. Good. Oh yeah, it's the only way to fly. Okay. Yeah, so we'll get to an important topic and we'll visit it over and over again. In fact, this is one of the places where I'll slightly break free just from Griffiths. We're going to talk about conductors, but there's one set of problem at the end in conductors that I will come back to after we discuss some important results in chapter 3 very shortly. Okay, but nonetheless, we should get started with the notion of conductors. What are conductors? Well, tell you what, let's start with examples. Can you give me, in this course, we're not conducting heat. What are you going to conduct? Electricity, charges, yeah? But I told you we won't get radical, we won't let charges move. Yeah, so hang in there. Yeah, but, so can you give me an example of a conductor? Platinum, it's very expensive. Aluminum, somewhere that is affordable and a good conductor. Copper, yeah.
What is expensive? It's just high society.
Yeah. That's hoity-toity. We'll settle for copper, right? So what that means, and there's a whole theory of why conductivity exists, and this is one of the topics studied in condensed matter physics. Okay, but electrons, as you know, exist in certain orbits, certain shells. Yeah, sometimes the way the geometry of charges and how they attach to each other, molecule by molecule, how that ends up being, what happens is in the outermost shell, there are electrons bound to the nucleus, but a slight nudge. And what happens is, so suppose you have one nucleus over here, and let's just talk about a simple array of nucleus, okay? And then you have, in the outermost shell, you have electrons over here. These are electrons. Okay, they're still bound to the nucleus, but the slightest nudge, what will happen is one electron is just happy to jump to here. So, but you can't have, all of a sudden a positively charged atom and a negatively charged atom. That's unsustainable. It'll go back. It has to be neutral. So what happens is another would go from here to here. As a result, you can get a flow of charge. And in some material, flow of charge is not expensive, easily done. The slightest nudge. And you can expect that's what we mean by conductors. These are not superconductors, yeah, but at the slightest amount of electric field, charges can move. Okay, now, and we can see how we can affect this motion by explicit example. Fine, charges can move. What happens then, I'll tell you how charges move, for example. If you take a conductor and you put a charge Q on it, immediately it's going to move. It's going to move in such a fashion that inside the conductor, the electric field is zero. Why? Because if the electric field is not zero, charges are going to move again. So it's going to rearrange itself so that electric field is always zero. And this happens very quickly, within a microsecond. You put charge on copper, a nice sphere, or even an awkward shaped piece of copper. You put charge on it, 10 to the minus 6 seconds. I don't know the number, but it's a very short period of time. The charges will rearrange itself so that all motion stops. This is just phenomena we see. We'll understand it more and more. Okay? It happens very quickly. How can it happen very quickly? I just told you what will happen is you put, let me even give you another example. So here you have a neutral metal conductor. And then you immerse this conductor in an external electric field. So what you would do is just say you have this band of external electric field. And this is E external. The charges are not too happy. They get pushed around. If you have positive charges, where would they go? Positive charges move along the electric field. And negative charges move? Yeah, it's minus QE, right? So what's going to happen is you have a positive charge built up here. Yeah? And the way to draw it, perhaps, let me tell you what, how diagrams would suggest this. So the way that I have drawn these positive charges suggests that the surface charge density is greater here, and then by fewer plus, they're spread out a little more, right? That means there's fewer charges over here. But this conductor was neutral to begin with. So if positive charges move to one side, the negative charges move to the other, equal amount. It's neutral, nobody's put charges on it. Again, and if I were being really careful, the number of negative and positive charges have to be the same. But now, guess what happens? Because of charge separation, these charges create their own electric field. Which way does the electric field point? Let me make this a straight line arrow. But this is the external electric field. What about these guys? They create an electric field. Charges emanate from the positive charge and goes towards the negative charge. And so you will get an internal electric charge. Now, what happens when you have equal and opposite electric field? So inside a conductor, when electrostatic equilibrium is reached, oh, that's a long sentence. When electrostatic is that correct? Equilibrium? That E net inside the conductor equals 0. I'm going to put the silly vector on 0, meaning all three components. So the net electric field, maybe this is 0.1. Look at the method. We're going to get a nice result now. And look at how elegant, how well the story is put together, right? When you write a story, it has to be tight, like the Silmarillion. You take away but a single sentence and things fall apart. Yeah? Now what happens is I'm going to consider a Gaussian surface. And then I'm going to do E dot dA. For any Gaussian surface inside the conductor in, oh my goodness, electrostatic equilibrium. What happens? Well, I know this. But that's just Gauss's law. But E inside, what is E inside? 0. And this is for any surface. Well, if it's true for any surface, that is true for any volume. If the integral of something is 0 for any volume, you can make it as big as you want to or as small as you want to. When can that happen? When the integrand is 0. In this case, what is it? Rho inside the conductor vanishes. Inside the conductor, I don't get to be descriptive in a physics course. This is one of the things I enjoy. It's like a story, right? We're done with the, well, we have math. You can't get away from math. What is another, so there's no net rho inside the conductor. There's another way of saying it. I'll say it as a third point. Any net charge density my diagram should be suggestive. Any net charge density must reside where? On the surface of the conductor. Very good. Now I can tell you what's the electric field on the surface of the conductor, by the way. Yeah? It's quite clear what happens. Charges must reside on the surface of the conductor. So let me ask you this. What we did here was we immersed this conductor in a bath of external electric field. Suppose we didn't do that. Suppose we just, transferred charge onto a conductor. It's easy to do, right? Run a plastic pen through your hair and touch a piece of metal with it. You have transferred charge. What happens to this charge? Immediately runs to the surface of the conductor. Never resides inside. Okay, I'm going to get to point 4. Yeah, it's just amazing how we use Gauss's theorem and learn all these properties of objects. Now what I'm going to do is construct my Gaussian pillbox. And I'm going to do this. And we did this, by the way. And what we have found was E perpendicular, let me do it this way, outside, minus E, well, we know better than that. We know better than that. This is just, remember the boundary conditions? But I just told you, inside, there's no electric field. Yeah? So on the surface, I can even write it vectorially. Point number 4. Yeah? So let me show you the diagram. Look, over here, it is positive charge. Sigma is positive, so it points in the outward normal. This is the from the example we did, this is above, this is below. That's the notation I'm using. So the normal is that way. So that means over here, the electric field perpendicular to the surface points this way. Well, how much is the magnitude? Well, it's sigma over epsilon naught. But over here, which way does it point? This is the limit as approached from the outside. I'm not saying that there's electric field inside. So there's a discontinuity. Electric field inside is 0, but you take the limit of the electric field, it points. That's why I wrote E up. You cannot, no one can read this on the screen, but it says electric field pointing out. Electric field pointing out. Not pointing out, electric field from the outside. Points inward. Do not mistake, there's no electric field inside. Okay. What does it look like? Good? Happy? A whole 6 minutes, and you're not quite ready for a sample problem. But I think I've been pushing you pretty hard. So we'll slow down for today.